All right, we're about to dive into one of the most profound, honestly, one of the most mind-bending ideas in all of physics. It all kicks off with a question that sounds like it's straight out of science fiction, but, and this is the key part, it's a question that scientists are taking very, very seriously.
Yeah, you heard that right. Is it possible that our entire three-dimensional reality, everything we see and touch, is just a projection? Kind of like an illusion of depth that's actually coming from a flatter, lower-dimensional reality?
And look, this isn't just some wild thought experiment. No, this is a real possibility that's being investigated at the absolute highest levels of theoretical physics. I mean, listen to this from Professor Kostas Skenderis. He's saying, imagine the entire universe. All the information that makes it up is actually encoded on a distant, flat 2D surface. Wow.
Okay, so let's get one thing straight right away. When physicists say hologram, they don't mean our universe is fake or some kind of computer simulation. Not at all. It's a bit more subtle. It just means that it might have fewer dimensions than it looks like it does. Think about it. All the information you'd need to describe our 3D world could be completely 100% contained on a 2D boundary.
So you gotta be asking, where does an idea this strange even come from? Well, it actually comes from a really deep conflict, like a fundamental crack right in the foundation of modern physics. You see, for the last 100 years or so, our understanding of the universe has been built on two amazing theories that are, well, totally incompatible with each other.
And here they are, the two heavyweights of physics. In one corner, you've got Einstein's general relativity. It's beautiful, and it perfectly describes the universe on the biggest scales. We're talking planets, stars, the whole fabric of space-time. And in the other corner, you have quantum mechanics, which is just unbelievably good at describing the weird, wild world of subatomic particles. They're both champions in their own arenas. The problem? Put them in the same ring and they just don't get along. They completely clash.
And that ultimate showdown, that clash, happens in the most extreme place you can possibly imagine, a black hole. A black hole is the perfect battleground because it's two things at once. It's incredibly massive, that's general relativity's turf, but at its very center, the singularity, it's infinitesimally small, and that's the home of quantum mechanics. It's the one place in the universe where both theories have to apply, and it's the one place where they both seem to break down.
And this is what brings us to the central mystery that sparked this whole incredible debate. We're talking about the black hole information paradox. So what is it? Well, in a nutshell, it's this. One of the absolute bedrock rules of quantum mechanics is that information can never, ever be destroyed. The details about something, its past, should always, in theory, be recoverable. But general relativity tells us that when something falls into a black hole, that information is just gone, forever. And for a quantum physicist, that's not just a problem, that's a complete deal breaker. It's impossible.
Let's walk through this, step by step. Okay, step one, imagine you drop a book into a black hole. All the information that makes that book unique, the arrangement of its atoms, the story on its pages, it all falls in. Step two, the great Stephen Hawking discovered that black holes aren't actually eternal. They leak something we now call Hawking radiation, and they slowly evaporate over time. But here's the kicker, step three. Hawking's own math showed that this radiation is totally random. It's just heat. It contains zero information about the book that fell in.
So, this raises a massive question. If the black hole eventually evaporates away into nothing but this random, featureless radiation, what happened to all the information from the book? Where did it go? According to Hawking's original theory, it's just gone. Poof. Destroyed forever. And that right there, that shatters one of the most fundamental laws in all of quantum physics.
Well, this paradox basically lit a fire under the entire physics community. It sparked a scientific battle that raged for decades, famously known as the Black Hole War. You had physicists turning into cosmic detectives, trying to solve this epic cold case. Where in the universe did the missing information go?
And I mean, this debate was fierce. Back in '75, Hawking's idea that information was destroyed sent total shockwaves through the physics world. But other physicists started pushing back. In 1993, a physicist named Don Page basically said, no way. If quantum mechanics is right, the information has to get out somehow. And he even described how it should happen in what we now call the Page curve. It all came to a head with a famous bet. And then in 2004, in a pretty dramatic turn, Hawking himself publicly conceded. He admitted he was wrong. Information, he agreed, has to be preserved.
But wait a second. Hawking conceding didn't solve the problem. In fact, it actually made it deeper. Okay, so if the information isn't lost, but the Hawking radiation is totally random, then how on earth does it get out? How does anything escape the inescapable pull of a black hole?
The answer? Well, it would require a complete revolution in how we think about space itself.
And that brings us right back to where we started, because the leading solution to this cosmic puzzle, and trust me, it's the most mind-bending one of all, is something called the holographic principle.
Okay, so what is the holographic principle? It proposes a truly radical idea. It says that all the information you need to describe a 3D volume of space, literally everything inside it, isn't actually in the volume. It's all encoded on its boundary, on the flat 2D surface that surrounds it.
Now, everything in our everyday lives tells us this should be wrong. I mean, our intuition says if you want to store more stuff, you need more space, more volume. The number of apples you can cram into a box depends on the volume of the box, right? More volume means you can store more information. Simple.
But here's where black hole physics just flips that completely on its head. When physicists calculated the absolute maximum amount of information you could pack into a region of space before it collapses into a black hole, they found something stunning. The limit, the maximum, it wasn't based on the volume. It was based on the surface area of the boundary around that region. Just the surface.
And that, right there, is how the holographic principle solves the information paradox. It suggests that the information from our book never actually gets lost deep inside the 3D black hole. Instead, it gets sort of smeared out and encoded on the 2D surface of the event horizon. So as the black hole evaporates, that information gets imprinted onto the Hawking radiation that's leaving, and it's preserved forever. It's just like the hologram on your credit card. All the information for a three-dimensional image is stored on that totally flat two-dimensional surface.
So think about this for a second. If this crazy principle is true for black holes, which are the most information-dense things in the entire universe, then, well, maybe it's true for the entire universe? Our huge, vast 3D reality could just be the holographic projection of information that's stored on some two-dimensional surface at the very edge of the cosmos.
And believe me, this isn't some fringe idea cooked up in a basement. It's become a cornerstone of modern theoretical physics. I mean, just in the last couple of decades, we're talking over 10,000 scientific papers have been published on the holographic principle. It's a really serious attempt to finally build that bridge between gravity and quantum mechanics.
And the really cool part is, we're starting to move beyond just pure theory. Physicists have been looking at the cosmic microwave background, that faint afterglow from the Big Bang, and they found that some of the irregularities in that ancient light are actually consistent with what you'd expect to see in a holographic universe. The real-world data from our universe actually fits the model. It's incredible.
And that just leaves us with one final staggering thought to chew on. If our entire existence really is a holographic projection, if this rich three-dimensional world is all emerging from a flatter reality, it begs the ultimate question, doesn't it? What and where is the screen? It's a question that pushes us to the absolute limits of what we can understand, and it suggests that the reality we all take for granted might just be one way of looking at a much, much stranger and more profound cosmic truth.